So we're looking at quadratic functions. This is lesson 3, analyzing quadratic functions, part 2, and we're on page 309 in your workbooks. So we've previously looked at the general vertex form with a being 1, and thus far we've looked at this form right here, which is y equals x minus p all squared plus q. And we looked at those parameters of what P and Q does, and just as a reminder, what is it that P does? P tells us our horizontal translation, and with that we knew that if it was a positive P value, then it would be translated to the right. If it was a negative p-value, then it would be translated to the left. With Q, we're looking at a vertical translation. And as expected, if we have a positive Q value, the quadratic will be translated up Q units, and if we have a negative Q value, it will be translated down Q units. So right now we're going to look at this parameter a when a is not equal to 1. Specifically for these first couple of examples, we're going to look at when a is greater than 0. So what they're starting us with here is the graph of y equals f of x, or f of x is equal to x minus 2 all squared. So again, you can see here that the p-value is 2, positive 2, and so that translates our quadratic, our parabola, 2 units to the right. When we look at the function y equals 2 f of x, then we want to rewrite that as y equals 2, so that's our coefficient, times x minus 2 all squared. If we graph that on our calculator, what we'll see is that we end up with a vertical stretch. So take a moment and put that into your calculators, and we'll come back in just a moment. Okay, so what we see here in the blue is our first quadratic, our first function, which is just our standard x minus 2 all squared. So that was the blue one right here, and that's been translated 2 units to the right. When we put in a coefficient of 2, what we end up with is a parabola that is skinnier. It's gone through a stretch factor of 2. And in fact, if you look at the table of values right here, the x values obviously are staying the same, but what's happening to all of my y values as compared to my standard, that comparison that I'm using, is that those y values are being doubled. So a factor of 2 has been applied to each of those y values. Okay, so if we sketch that on, normally we know that with our vertex, we would go 1 over and 1 up. Remember, if we've got y is equal to x squared, and so when we've got that being doubled, instead of 1 over 1 up, we'll go 1 over 2 up. 2 over instead of 4 up, we'll go 2 over and 8 up. Because we know that the vertex has the axis of symmetry passing through it, then that also helps me to plot the other points, and I can draw the smooth curve going through, and that extends all the way up, continuing. So we'll put some arrows on the end and just label that as y is equal to 2 times x minus 2 all squared. When we graph the second one, let's take a look at what happens there. So when we enter in 1/2 of x minus 2 all squared, we can see this black parabola, and what's happened compared to the original, which was the blue, is it's now gotten wider. And so we sometimes call that a vertical compression. If you look at the table of values, again, just look at the blue and the black. So when y was 4, y is now 2. When y was 1, it's now a half. Half of 0 is obviously still 0. And half of, if we go up to 25, is 12.5. Half of 36 is 18. So we've taken half of all of our y values. So again, going back here, if we're representing this in its equation form, so we'll take the coefficient, 1/2, and then f of x was x minus 2 all squared. So it's y equals 1/2 times x minus 2 all squared. If we're sketching that out, then again, our usual was over 1 up 1. Instead, we go over 1 up a half. Over 2 is usually up 4. Instead, we'll go over 2 and up 2. Whoops. And then over 3 is typically up 9. Instead, we'll go up 4.5. And so on. If we go over 4, typically it's up 16, which is off my my grid right here, but now instead we're going over 4 and just up 8, and so that will fit on my graph. And again, using that axis of symmetry that passes through the vertex, that's not changing. I can then plot these points on here with some accuracy and join these points together. So again, continues upwards, and we'll label that y is equal to 1/2 x minus 2 all squared. So if we fill in the blanks, compared to the graph of y equals f of x, or y equals x minus 2 all squared, the number 2 in the graph, so that coefficient represents a vertical expansion, so it's a vertical stretch by a factor of 2. The y-intercept, before the y-intercept of y equals f of x was 0, 4, but now our y-intercept is right here, and it is 0, 8. So it is double that. If we look at the other graph with a coefficient of 1/2, we're now looking at a vertical compression, so it kind of gets wider by a factor of 1/2. And the y-intercept, again, the original y-intercept was 0, 4. Our current y-intercept is right here, and that is 0, 2. And so the y-intercept, when our coefficient is 1/2, is going to be half the y-intercept of the other graph. So we typically, as I've been calling it, it is a stretch factor, and the stretch factor is anchored by the x-axis, and that tells us that the x-coordinate will not change. The y-coordinate is going to be multiplied by the factor of a going through it. So the parameter then is going to be, A is going to be a vertical stretch factor of A. Okay, so if A is greater than 1, then we're talking about a vertical expansion, so it gets skinny. And if A is greater than 0 but less than 1, then it goes through a vertical compression, or in essence, it gets wider. So let's take a look if A is now less than 0, meaning that A is going to be a negative value. So if f of x, if we're back to y equals x squared, then if we apply a negative coefficient, we're looking at y equals negative x squared. And in this case, we're applying both a negative and a factor of 2, so y is equal to negative 2x squared. So let's take a moment and put those into our calculator to see what the effect is. So we can see I've got y1 is just your standard function, y equals x squared. That's in blue, so it opens up with the vertex on the origin. As soon as I apply a negative as my coefficient, then you can see it immediately just reflected over the x-axis. And so literally, if we look at the red column here in the table of values compared to the blue, every value is exactly the same. It's just simply its opposite. So it is just the reflection over the x-axis. As soon as we apply a coefficient of -2, not only is it reflected opening downwards, but it is also stretched by a factor of 2. So if we take a look here, if we were to graph these, again, if we were to use this without going back to the calculator, I know that if I'm just applying a reflection, the vertex is staying in the same spot at the origin. I'm over 1, down 1, over 2, down 4, over 3, down 9. That's 5, there's 9, and then again our y-axis serves as the axis of symmetry, and so we can sketch in that graph very easily. So that is y is equal to -x squared. As soon as we put in the stretch factor of -2, so over 1 instead of down 1, we're down 2, and over 2 instead of down 4, we are down 8. And again, drawing that in, so you can see that it does seem to get skinnier or stretched out, and so that red one is y is equal to -2x squared. So let's take a look then at the table. If you want to hit pause and then come back to it, and we can go through. So let's take a look at our answers. We have already written those equations. The vertex isn't moving because we don't have any p or q values other than 0. And because there is no horizontal translation, then the equation of the axis of symmetry isn't changing. What is different now, though, is our maximum and minimum value. So instead of having a minimum when the parabola opened upwards, because it's now opening downwards, we have a maximum. So the values can't be any higher than the q value. And since there was no vertical translation, then the q value was simply 0. So the description, when we just had a -1 as our coefficient, we're just looking at a reflection over the x-axis. When we throw in a -2, then not only do we have the reflection, that's a negative, then we also have a vertical stretch factor of 2. So how does the graph compare then? Is that it is a reflection in the x-axis. So if we look at filling in a few blanks, we've already stated this a number of times, so compared to the graph of y equals x squared, the graph of y equals ax squared, where a is less than 0, results in a reflection in the x-axis and a vertical stretch by a factor of a about the x-axis. So if we now take a look, this next bit here is essentially just our summary. So if we're looking at putting all of these pieces together with A and P and Q, then these are all of the pieces that we need to consider. So A gives us not only our vertical stretch, it also tells us if there is a reflection, and because of whether or not there's a reflection, we can also tell, does it open up or down, and therefore as a result, is there a minimum or a maximum point? We know that P indicates the horizontal translation, Q is the vertical translation, P and Q are the coordinates of the vertex, and x equals P is the equation of the axis of symmetry. So all of these will be asked of you guys over and over again when you are given that vertex form, and so there's lots and lots of information within that form. So let's take a look at class example number 1 then. So if we have the function 2 times x plus 4 all squared minus 3, so let's take a look at what's going on here. So we have that a value is positive 2, so that means that we have a vertical stretch by factor 2. Okay. We know that our p-value is going to be -4. So p is equal to -4. And what does that tell us? That means that we're moving left 4 units. Because our q value is -3, that then gives us our vertical translation, which is down 3 units. Other things that I'd like you to say about this, so certainly if we're just stating transformations, you'd be done at this point, but just little things to think about as well. Since our a value is positive, we know that it opens up. We know that if it's opening up, there is then a minimum value, and the minimum value is dictated by our vertical translation. So since it's coming down 3 units, and the minimum is -3. As well, the vertex is based on the translation as well. So horizontally, we're going left 4, so -4 and -3. And our axis of symmetry, the equation for the axis of symmetry is based on our horizontal translation, and that is then x is equal to -4. So those are additional pieces of information that you will need to provide. So let's take a look at Marika and Curtis. And so in terms of discussing how to graph this function without using a graphing calculator, it's interesting because there's a few ways to go through this, and when I first went through it, I actually thought, well, Marika and Curtis, well, they could both do it either way, and that's because I'm just doing by graphing and just by counting, and recognizing that as soon as I look at the stretch factor, then regardless of where it is being translated, that parabola will be congruent to the original stretched parabola. But if we're thinking about it from the standpoint of where each of these points lie and their coordinates, then one is correct, the other is incorrect. So let's take a look at Marika. So Marika is going to do her stretch first. So again, that means that the x stays the same, we're changing the y. So normally I would be going 1 across 1 up. Because the stretch factor is 2, I'm going 1 across 2 up, 2 across instead of 4 up, we're going 8 up. Because the axis of symmetry is my y-axis, then I can go ahead and plot those other points. And there is that stretch factor happening. And so now we want to translate it left 4 and down 3. So if we go left 4 and then down 3, here's my vertex. So again, from that point, I can either take the points I've already found. So for example, I can take this one and translate that 4 units over and then 3 units down, or I can just start counting again. So 1 over, 2 up, 2 over, and 4 up, and 3 over, and instead of 9 up, we're talking about 18 up, so that's quite a ways. So that's going to be off my page, I think. So again, with a, didn't work out quite as well as I thought. bit odd right now. Let's see if I can fix that up a bit. There we go. Okay, and so at this point we are looking at y is equal to 2 times x plus 4 all squared minus 3. So for Curtis, if Curtis was to translate it first, so now we're moving it to a vertex of -4, -3, and so then standard y equals x squared, so 1 over 1 up, 2 over and 4 up, and 3 over and 9 up. You can draw in Curtis's. That has been translated. So this is y is equal to then just x plus 4 all squared minus 3. So now if we take a look at stretching it after the fact, at this point my y value is -3. So the x value isn't changing, but if I apply a stretch factor of -3, instead it's going to be at -6. If I look at this point right here, the x value isn't going to change, so it's still at -3, but the y value is at -2. Instead, multiplying that by a factor of 2, it'll be -4, sorry. And with that axis of symmetry, in this particular case, then I've got a y value of +1, and so then my y value is going to end up being +2, and then we can draw that at this point. So this is then Curtis's, and so we can see that it's obviously very different than Marika's. Marika's is the correct one. Okay, so Marika is correct. Okay, so if we're using Curtis's coordinates specifically, at the same time, if you wanted to translate it first and then just start with the vertex and count from the vertex, that will work. So if I went from Curtis's and we moved the vertex and the vertex stayed fixed, then we said, okay, I'm stretching this by a factor of 2, then I'll go over 1, up 2, over 2, instead of up 4, I'll go up 8, then Curtis would be fine. But if we're doing it algebraically, we have to stretch it first. Okay, so I'll just make a note of that here for you guys. So, if graphing and just counting, counting on the grid, then order won't matter. Okay. So essentially what are we doing is we're translating the vertex and then stretching it from there, stretching the original one from there, but algebraically, so we must stretch, oops, and this is not there, we must stretch first, okay, then we can translate and then reflect, okay, or you can reflect and then translate. But the important part will be to stretch it first. Okay, so for example, let's just do a quick example that's not in the book. So if, for example, if I was to take this point right here, actually let's do 2, 4. So example, if we take 2, 4, that point on x squared, okay, equals y, so y equals x squared, where will this point end up? Where will this point end after the translation, or all the transformations? Okay, so the very first thing that we're going to do, so if I've got 2, 4, so the very first thing we're going to do is stretch. So that is going to be, that was a factor of 2, because we had y is equal to 2x squared. So then that means that everything is going to get doubled for your y. So then that means the x is not changing. Remember, the x is anchored. So we're talking about 2, 8. At the next part is we're going to translate. So we had said 4 units left and 3 down. So that now takes into account 2, and then that's x plus 4 all squared minus 3. So that would be then 4 left is going to be negative 2. 3 down is going to be 5. So that point 2, 4, once it's been stretched and then translated, will end up at negative 2, 5. So if this was point P, this is point P primed. Okay, so let's take a look at class example number 2. Okay, so if we take a look, we've got, in this particular case, P and Q are 0, so the only things that we see happening is we've got a negative A value, so we've got a reflection and a stretch factor of 1/4. So vertical stretch factor of 1/4 and a reflection. So rearrange B and then hit pause, and let's come back and see what you've done. So in the second one, we're going to rearrange it to isolate y, so we can multiply both sides by 3, so y is equal to 3 times x plus 6 all squared. That tells us that there's a vertical stretch factor of 3, and the p-value is negative 6, so we're going left 6 units. Okay, let's take a look at class example number 3, and it says the following 3 transformations are applied in order to the graph of y equals x squared. So we've got a reflection, and then we have a vertical stretch, and then we also have a translation as well. So at the end of 3 transformations, the point 1t is on the resulting graph. So find the equation of the image function after each transformation. So first off, we have y is equal to x squared. So if I complete the reflection, what happens is all of a sudden now we're looking at negative x squared. If we have a vertical stretch factor, then now we're looking at negative 1/3 times x squared. Translation, 7 units right. That's going to be our p-value, so we will have then y is equal to negative 1/3 times x, and if I'm going right, then p is positive 7, so it's x minus 7 all squared. So the coordinates of the vertex, well then the vertex is always going to be PQ. So then in this case, P is equal to 7, Q is 0. So if I'm talking about the value of t, what are we looking for? Is we're looking at when x is equal to 1, then if we have, so 1t means that x equals equals 1. Since we already have our equation, we know that it's y is equal to negative 1/3 times x minus 7 all squared. So then y is equal to negative 1/3 times 1 minus 7 all squared. So y is equal to negative 1/3 times negative 6 all squared. And that is then negative 1/3 times 36. And negative of 1/3 of 36 is then negative 12. Okay. So take a moment and work through class example number 4. So let's take a look then. So our first function is negative times x plus 3 all squared minus 4. So our vertex is always PQ. So that means it's negative 3, negative 4. Because it has a negative a value, that means it opens down. And so it has a maximum. That maximum is the same as your q value, which is negative 4. The equation for the axis of symmetry is x equals p. We're looking at the p value of the vertex, or the x value of the vertex, so x is equal to negative 3. The domain is x is an element of the reals, so there's no context, so that means that we're talking about it opening downwards, and it's just going out and out and out, so x is an element of the reals. For our range, all of our possible y values, it's a set of y values such that y is less than or equal to negative 4, since negative 4 is our maximum, and again, because it is a solid line curve going downwards, then y is an element of the reals. For the second one, again, our vertex PQ, since we don't have a constant being added on the end, q value is 0, so that's why we're looking at 9, 0. Our a value is positive, so our stretch factor is positive 3. That means that it opens upwards. That means a minimum, and the minimum is 0. The equation of axis of symmetry is x equals 9. Domain again is x is an element of the reals, and the range is y, set of y values such that y is greater than or equal to our q value again, which is 0, and y is an element of the reals. So please take a look at your homework assignment and let me know if there are questions.